Good morning, everyone. I am Kushagar Singh, technical member of Mars Foundation, and today I'll be your host for this webinar on machine learning and artificial intelligence for EV motor design, an initiative taken by Mars Foundation, the Mobility Alliance, and Social Sustainability Foundation that has the motto "Driving with Agility Towards Sustainable Mobility." I would like to I would like to welcome you all on this beautiful morning, especially our prestigious speaker for today. Now, before we move forward, I'd like to tell everyone that if you have any questions on this webinar, then you can put it in the chat box, and we'll make sure to take it up after the speaker is done with his presentation. So let's move forward. Before that, I'd like to tell you all about our mission at Mars Foundation, which is to enable sustainable mobility ecosystem, and our vision that is to become the country's largest platform, enabling its stakeholder in the sustainable mobility ecosystem. And keeping the mission and vision in our mind, for the last 1.5 years, we've held more than 10 events and engaged with various startups and their companies. We've also trained more than 30 mechanics to adapt to the latest EV technology in the automotive industry. Now, starting with today's webinar, we have a speaker for today, which is Dr. Praveen Kumar. Now, Dr. Praveen Kumar completed his BTech from NIT Hamirpur, his MTech from IIT Delhi, and has a PhD degree from TU Delft in electrical machine design. He's currently a professor at IIT Delhi and also the owner at Desha Technology Private Limited. He, in his background, previously he has been an associate professor at IIT Delhi and also an assistant professor, same at IIT Guwahati. He's been associated with IIT Guwahati for more than 12.5 years. He's also been the co-founder and the chief technical officer at ElmoCAD, the development engineer at Trimeris GmbH, and a development engineer at Dior AG. Welcome, sir. Now, I'd like to now hand over the screen to Dr. Praveen Kumar, if he'd like to share the screen.
Yeah, thank you, Kushagra. So I'll just try to share my screen, and please do let me know if you can see it.
Sure, sir.
I hope is my screen visible to you all?
Yes, sir, it's visible.
Okay. So then, yeah, we can go ahead with the theme for today's talk. So today we will be, or I'll be talking about how we can apply AI, the artificial intelligence and machine learning to the problem of motor design. So that's a rather new project that we have started. It started last year actually, and it's been continuing so far. And there are 3 PhD students who are involved in this project and are contributing towards the development of the entire design platform. And I'll be giving you a brief summary of what exactly this entire idea is. So it's still in the nascent stage and it's evolving, but let's see where we are today with it. So if you look at the motor design problem that we have today, so usually we get a problem statement that we have a specific vehicle platform and we have a desired drive cycle, and for that drive cycle we would like to know what kind of a motor would meet the requirement. Okay, so with these two very high level inputs we have to come to the entire design of the motor. So that's the usual problem statement that we encounter when we work with EV drivetrain. So it's not just the motor, but eventually the converters, the battery pack, and so on. But today's talk would be focused on motors, that how do we come from these two very high level specification to a detailed design of the motor. Now, what happens today is that, or today the process that we follow in our group is something like this. So first of all, we do a very detailed drive cycle analysis for the given vehicle platform. From there, we try to determine the motor specifications like the torque versus speed curve, the rated values of torque, the peak values of torque, the base speed, the maximum speed, and so on. So we try to determine all the major motor specifications. Then the next step that we take is to work with the equivalent circuit of the machine. So if we are working with induction machine, then we take its equivalent circuit. If we work with, say, PM machines, then we take the corresponding equivalent circuit, and then we try to determine the equivalent circuit parameters which would fulfill this requirement, the torque versus speed requirement. Okay, so it's a inverse optimization problem. So we need to know each and every, or we try to find each and every equivalent circuit parameters to meet the requirements that are given by the step number two, or that we get from the step number two. Now, once we know the equivalent circuit parameters, the next challenge is to find out the motor geometry which satisfies those equivalent circuit parameters. So, for example, if we need a certain value of the inductance, let's say stator leakage inductance, to meet the torque versus speed requirement, then we would try to find out the number of slots in the machine, the dimensions of the slots, which will give us that inductance value, because inductance value is given by the geometry of the slot of the machine. It is given by the shape and size of the slots, and that is how we then determine the equivalent circuit parameters. So for a given set of equivalent circuit parameters, actually there is a unique geometry of the machine. So the challenge is to find that unique geometry. Okay, and that is again a very, very iterative process, and a very, very time consuming process. So once we have the geometry of the machine that satisfies the equivalent circuit parameters, then we go into the final stage of the finite element analysis, where we try to perform the detailed simulation on the motor. We try to find out its magnetic field distribution, the flux distribution, the efficiency maps, and so on and so forth. So these are the major 6 steps that we take today to find the proper design which would meet the requirement. So you can see here there are two very, very critical stages. So one is to find the equivalent circuit parameters which would satisfy the desired characteristics, and the second is to find the geometry of the machine which satisfies the equivalent circuit parameters. Okay, and these two steps, they consume the maximum amount of time. Okay, and it also needs a lot of know-how on the part of the design engineer. It also needs a lot of experience on the part of the person who is designing the motor. So now the question comes is that, can we really reduce the time to design using any kind of AI and machine learning based technique? So, to come to that, we first need to understand what kind of mathematical models do we use in each stage. Okay. So, in the first 3 steps of the machine design, which is the drive cycle analysis, motor specification determination, and the equivalent circuit parameter estimation, we use these 3 types of mathematical models. We use exact physics based models to define the motion of the vehicle. So that is all Newtonian physics. We use those models. Then we use statistical analysis to find out what is the desired or the optimal torque versus speed characteristics of the machine. Okay, it's statistical analysis because we want to make sure that the machine is neither predominantly overloaded nor is it predominantly underloaded. So all that can be done by statistical analysis. So we need statistical models for that. And then to find the equivalent circuit parameters which would meet the motor specifications from step number 2, we need optimization. So we use any kind of classical optimization techniques like gradient search method, or whatever deterministic techniques that people have proposed to do the optimization. So it's a multivariable optimization. There are 6 7 unknown parameters, and you have to optimize, find the optimal value of those 6 7 parameters to get the desired torque versus speed characteristics. So these are the 3 types of models that we would use in steps number 1 to 3. Then comes the step number 4, where we need to get the parameters of the geometric parameters of the machine which would satisfy the equivalent circuit parameters. Okay, Now, here we need empirical models because having an exact mathematical model is practically impossible because machine is a highly nonlinear system, and for any nonlinear system it is extremely difficult to make an exact mathematical model, because even if we try to make an exact mathematical model, it will be so complex that we won't be able to solve at the end of the day. So we need to work with the empirical models, and then we need to have a lot of design experience because that will enable us to come to a solution very fast based on the previous experience. And also we would need a lot of engineering judgment. The engineering judgment is necessary to evaluate the design that we have come up with, whether that design would be manufacturable, whether that design would have the required mechanical integrity, whether the machine that we are creating would be noise free, or would it have a lot of noise in it. So there are many such judgment issues that would come up, and they need to be addressed, and the entire process is extremely time consuming. Okay, it's very time intense. And in the last stage, where we do the fine tuning of the machine using finite element analysis, that is extensively time consuming. It's computationally expensive problem, and apart from that it takes a lot of time. So now the question comes that how can we reduce the time at each stage? That's a challenge. How can we come to a solution faster? The second is, how do we minimize the role of design experience and engineering judgment? And that especially becomes very important in a new team or in a fresh team. So for example, there's a startup, or a company decides to go into electrification, so they might not have a long history of design of motors and converters and things like that. So they do not have the in-house engineering judgment, nor do they have the in-house design experience. So how can we overcome that problem? And also empirical models are as good as the experimental observations. So if a team has done lots of experimental observation, then their empirical models are more robust. A team which has not done extensive experimentation in the past, then they would not have a very rich empirical model. So how can then we still come to a design where the proper or robust empirical models are not available? So what do we do here? So the idea was that if we try to merge the domain expertise, okay, here the domain expertise is machine design, together with the upcoming field of artificial intelligence and machine learning, then that intersection that we get is actually the intelligent design platform. So we are trying to blend the domain expertise of motor design together with the AI and machine learning algorithms, and then create a design platform which would minimize the time to design the machine, which would minimize the use of empirical models, which would minimize the use of engineering judgment, and would also minimize the role of prior experience and expertise while coming to a solution. So that is the big goal and the idea that we have. So apart, I mean, engineering judgment and previous experience is still important, okay, but it's not a key parameter if this kind of a intelligent platform is made properly, okay, because the previous historical judgment and the historical experience is actually captured by the AI algorithms. Okay, so it's there in form of the algorithms, and it is accessible to the young generation of design engineers and across the generations. And moreover, it can also become self-learning. So more and more it is used, more and more enriched it becomes with time. So it's also the self-learning aspect which makes the AI very important and a very attractive proposition. Now, to understand how we try to use it, let's take an example. Yeah, I think somebody wanted to say something in between. I heard some question.
Sir, I think Harishankar sir accidentally
Oh, okay,
unmuted himself.
fine.
You can.
Okay, then. Yeah, let's carry on. So let's take an example, and the example that we are going to take is here. So there is a situation where we need a motor which produces a maximum power of 21 kilowatt at wheel. Okay, so that's the power requirement at wheel, and the maximum torque required at the wheel is 41 kilonewton meter, and the maximum speed of the wheel is 2080 rpm. So this was the requirement at the wheel. Now the other requirement that we have is the ratio of the maximum speed to base speed for the motor. Okay, so this point where up to where the torque remains constant. So if you see this orange curve or even the green curve, so the duration or the speed up to which the torque remains constant is known as the base speed, and the maximum speed of the machine is where it produces some amount of torque. Okay, so beyond that the machine can't operate. So the ratio of the maximum speed to base speed is taken to be 3. Now that depends on the choice of the controller that we are going to use. So if we use any kind of a scalar control technique for the machines, then this ratio of maximum speed to base speed is hardly 1.2 or 1.5. If we use state-of-the-art vector control techniques, then the ratio of the maximum speed to base speed comes to around 3. And that's what we have used here. 3 is the ratio. And also the peak power to the rated power, so that's taken to be 2, and which is a very good number if we are considering any kind of a liquid cool machine. So the idea is that if you have a 50 kilowatt motor, for example, you can overload it by a factor 2, or you can overload it by 200%. So that means you can extract 100 kilowatt power for a short duration of time. And this is the difference between an internal combustion engine and an electric motor. So an ICE cannot be overloaded, whereas a motor can be overloaded for a short duration of time. And 200% or factor 2 is a very comfortable number for any kind of a liquid cool machine. And the overall gear ratio for our problem was around 1:12. Okay, so now if we take the values that the wheel needs, and if we take the gear ratio, then we come at the specifications of the motor. Okay, so the rated power of the motor is around 150 kilowatt. The rated torque is 1 kilonewton meter, or 1081 kilonewton meter. The peak power that the motor needs to produce is 300 kilowatt, and the base speed of the machine is around 1324 rpm, and the maximum speed is 3973 rpm. So we have more or less the detailed specification of the machine. Now the question comes that what should be the design of the machine which would give us these numbers. So when I say design of the machine, it means how many poles, how many slots on the stator, how many slots on the rotor, what is the diameter of the stator, what is the diameter of the shaft, what is the length of the machine, what is the air gap. So every detail we need, so that the design of the machine satisfies these 5 parameters, these 5 numbers. Now, to do that, we go through our now AI based design approach. Okay, so to do the AI based design approach, so we need up to this point the torque, power, and speed characteristics, which we already have, by the way. Okay, so all this analysis is done, and then we have all these parameters, the 5 parameters which would be needed. And now once we have those critical 5 parameters, we come to the AI domain. So we have the desired torque versus speed characteristics. Those 5 parameters, they give us the entire torque versus speed characteristics, and we have the motor specifications. Okay, the rated value, the peak value, we have all that. Now these inputs, they go to the first artificial neural network. ANN is the short form for artificial neural network. Now the output of this first artificial neural network are the major motor design parameters. Okay, like the length, the diameter, the number of slots, the number of poles, and so on and so forth. So the major parameters of the machine. Now, the parameters that come out of the artificial neural network, they go through a parameter consistency check or sanity check. Okay, because it's possible that the ANN gives us that the machine should have 5 poles. Excuse me. So now 5 poles is an absurd number because the number of poles in a machine should be an even number. So such kind of sanity checks have to be performed. Okay. Ideally, the ANN model should not give us such kind of a value, but still to be double sure, we do some kind of a parameter consistency check. The other example can be that the algorithm gives that the stator should have 37 slots. Now, that's again a strange number because the number of slots on the stator should be divisible by 3 if we have a three-phase machine. Okay, so to avoid any such kind of strange or arbitrary values, we do a sanity check on the results that the ANN model gives. Now, if all the parameters they pass the sanity check, okay, then we pass them to the second ANN model, and the output of the second ANN model is actually the stator lamination design. So it gives the details of the stator lamination, that how the slots look like, what are the dimensions of the slots, and so on. Now, we have to appreciate that there are multiple slot geometries or multiple slot shapes that are possible. Okay, it is very likely that the ANN2 or the artificial neural network model number 2 gives a specific shape and size of the slot. It is also very likely that the design team thinks that we do not want to use this slot because maybe manufacturing that specific slot might be expensive, or maybe we don't have a die for that slot today. We would like to use an existing die. So in that case, there should be a possibility for the design team to tweak the result that the ANN model 2 gave. Okay, and that is the part which we call as slot geometry translation. So whatever the ANN model gave can be accepted as it is, or it can be tweaked. Okay, so once we tweak it, then we need to follow certain rules and guidelines. So we can't do an arbitrary tweaking. So the tweaking is then controlled by a set of rules. Again, these are all empirical rules. They have to be followed, and and remaining within the framework of these empirical rules, we do the tweaking of the slot geometry. We call it as slot translation. And once we are satisfied with that, then we get a geometry of the stator which is semi-optimized. So we don't claim it is an optimal design yet because we don't even know what the mathematical optima is. Okay, so to avoid any kind of false claim, we say that yes, it is a semi-optimized model, because finding an absolute global mathematical optima for a given problem is virtually impossible. Okay, it needs tremendous amount of computing. So we would never know what the actual optima is, but then what we get is very, very close to the optimal solution. At least that claim we can make, and that's why we use this term semi optimized stator lamination design. So now, to train the ANN, this was the kind of a data set that we use. So you see here, there are two artificial neural networks that I used just for this data. So these artificial neural networks have to be trained on pre-existing machines. So this was the data set that we use. So we had machines up to 25 kilowatt. There were 9 samples, 9 existing machines with lots of measurements done on them. Between 25 and 50 kilowatt, there were 25 machines that were available with the data. And then 50 to 75 kilowatt, there were 18 machines. So this was the set of different power ranges that we had for the machines, and it went right up to 250 kilowatt. And also, if you can see, for different voltage ranges. So for our EV application, it's 0 to 1000 volts. So that is enough. Beyond that, these are all very high power, high voltage industrial motors. So for us, the important voltage range was from 0 to 100 volts, and there were 0 to 1000 volts, I'm sorry, and there were 237 samples that we had. Because today, if you look at heavy vehicle platforms like buses or trucks, EV buses or trucks, then 800-volt platform is becoming quite a standard. Okay. And then for the speed ranges, different speed ranges of the machine from 0 to 400 rpm, or 400 to 800 rpm, and so on and so forth, right up to 4000 rpm. So these were the number of samples that we had. So we took all these samples, and then we started to train the neural network. Now, in the initial stages, the training of the neural network took maximum number of time. Okay, but once the neural networks are trained, then you get the results in the new designs in matter of seconds. You don't need too much of time. So it's a one-time effort to train the neural network. And here is the model of the first neural network. Okay, so I told you in the first neural network, we give very high level specifications of the machine, like output power, voltage, frequency, rated speed, and so on. Then there was a hidden layer of neurons, and there were 15 nodes there. And then these were the 10 outputs. Okay, so these 10 outputs were the global design parameters of the machine, like stack length, number of poles, stator number of slots, rotor number of slots, and so on. Okay, so the major parameters, design parameters of the machine. So with these four inputs, we could get these 10 outputs, and this was the hidden layer of the neural network. Now, to train this neural network, we use the previous data. Okay, and then the training means we were looking at how many nodes are good enough, what kind of functions that we would be using between the interconnections, and so on. What kind of training algorithm do we need to use? Is it getting overtrained, or is it undertrained, or is it optimally trained? So all that was done, and it took us almost a month or more than a month to train the neural network for the first case, the ANN1. Now, you see, this is how the parameter consistency check looked like. So, for example, these are the output parameters that the ANN gives once it's properly trained. Okay, then each of these parameters, they pass or they go through a consistency check. So, for example, we should not have same number of slots on the stator and the rotor. Okay, or the number of slots on the stator and the rotor, if you take the difference of these two slots, then it should not be equal to integer multiple of number of poles, because that will then increase the noise in the machine. It will increase the crawling of the motor. Okay, so these are all some empirical rules that need to be followed. Okay, so if the neural network gives any of these conditions, then we don't accept those number of slot combinations. We rather change the number of slots on the stator and the rotor, or we decrease the number of slots on the stator and the rotor to avoid these kind of ratios. Okay, in our design, in these designs, this is already taken care of, because the people who designed the motors, they did pay attention to that. But still, something might go wrong when we get the results. So to be sure, we put these kinds of checks. Okay, so this is the first level of checks that are put, and all the outputs need to pass through these checks. It's an illustrative example that I have given here. The library of checks is rather larger, much larger than what we have here. Now, you see, after going through the consistency check, so these are the major output parameters. So we gave these input parameters from the initial analysis, which I showed 6 slides back. And these are the 10 outputs that we have: the stack length, the number of poles, the number of stator slots, the number of rotor slots, and so on. And also the slot type. So slot type represents what kind of a slot geometry are we looking at. And then what are the flux densities in the key parts of the machine. Okay, so we got all the key parameters. Now, we take these key parameters and pass on to the second neural network. Now, this second neural network is also trained using the big data set which I showed you earlier. Okay. Now, the job of this second neural network is to take these parameters, okay, and give us the detailed stator design. Now, to do that, the entire neural network was trained. And if you see here, this neural network is much more complex than the neural network one. It has 3 hidden layers. It accepts 10 outputs. I didn't write all the 10, but it accepts 10 inputs and gives us 9 outputs. And the outputs that this neural network gives are very, very detailed designs of the stator and the rotor lamination. Now, training this neural network again took a lot of time because it's a very complex one. The algorithms take huge time to execute and run. Okay, so again, it's a matter of many weeks to train properly this neural network. And once it was trained, then it gave all the excuse me, detailed parameters of the stator lamination design. We gave the major input parameters and we got the detailed design, like the illustration is given here. So what is the depth, length of width of the slot, what is the depth of the slot, so on and so forth. Now, as I told you earlier, so the output given by this neural network might not be acceptable to the design team. The design team might like to go for different kinds of a slot. Okay, and we should give that discretion to the design team. So we come to the slot translation part. Okay, so this was the kind of a slot geometry on top that the neural network gave, but we don't want to accept it. We want to take some other slot geometry. So one can choose any one of these slots here. These are just some samples that I have given, but we actually have a library of around 80 plus slots. Okay, so now to translate this slot into any one of the 80 types of slots that are feasible, we again need to follow some rules. So the first rule that we need to follow is that the slot area should not change. Now, if the neural network model gave a slot with a certain slot area, then if you want to choose any other slot, then the area of that new slot should be exactly same as this slot. There can be a small variation, maybe 1% or under 1% variation. Okay, because when we do the geometry translation, it is not always possible to have exactly the same slot area. A small deviation is allowed, but yes, it should not be more than 1%. Clear? Then also we need to make sure that once we translate this specific geometry into any other geometry, the inductance, the leakage inductance of the slots should not change, because if the leakage inductance changes, then we are changing the entire behavior of the machine. Okay, so that should not change. So these are some of the rules that we need to follow when we do the slot translation. So keeping those rules in mind, the algorithm can do any kind of a slot translation, and one can choose any other shape of the slot, and one need not accept the slot shapes that is given by the neural network. Now, once that is done, then we come to the rotor part. So we have the detailed lamination design of the rotor. We need to know now, we have the detailed lamination design of the stator. So we now need to know the lamination design of the rotor. So if we recall, let me go back a few slides. So if you recall, this was the output of the ANN1, okay, which gave us the major motor parameters, okay, and the major motor parameters were these here. So we take these parameter sets, okay, we take this set of parameters and we feed it to the neural network 3, and the output of the neural network 3 would be the rotor lamination design. Okay, depending on what is the speed of the machine, what is the output power of the machine, and so on and so forth, we get a detailed rotor lamination design. Now that rotor lamination design again has to go through a consistency check. Okay. And also the user might accept the design or the slot shapes that the neural network gave, or may decide to use some other slot shape, just like in case of stator. Okay, so that is allowed. And once the user is finally, or the design team is satisfied, then we get the semi optimized design of the rotor. Now, to understand that, here is the neural network 3 that we have. So this neural network 3, which gives us the detailed rotor design, has one hidden layer, okay, of 20 nodes. It accepts 7 inputs and gives 13 outputs, and these 13 outputs define the entire detailed geometry of the rotor slot shape. Now, if you see here, you would appreciate that all the 3 neural networks have a very different structure. Okay, they have a different level of complexity, and that is so because each problem is a unique one. From high level input to the motor major motor specifications is one problem with a complexity. Now, motor specification to detailed stator lamination design is another problem with another level of complexity. Now, motor specification to rotor lamination design is a third problem with a different complexity. Okay, but then all these 3 neural networks are trained using the same data set which I showed you earlier. Okay, the data set remains consistent, and all the 3 neural networks are trained using those input data set that we had. Now, having said that, let's look at the output of the neural network 3 for our test example that we are looking at. So this is what the neural network gave for the rotor lamination, and it gave all the details of the slot geometry. Okay, now again, the design team can accept this slot geometry, or can decide to go for some other slot geometry. Now we have a, library of around 30 or 35 rotor slot geometries. So one can translate any geometry into any other geometry. And while we do the translation, we again need to keep the important points in mind, that the slot area should not change and the leakage inductance of the slot should not change. Because if the area or the leakage inductance changes, then we are changing the entire behavior or the property of the machine. Okay, so that we should try to avoid. And once we have chosen this slot and all fine tuning is done, then actually we have the complete design of the machine. Now, if I exclude the time to train the neural network and look at this entire design process, then from the point of giving the high level specifications to getting the final design of the machine with all the details of the slots and stator slots and rotor slots and so on, takes 5 minutes, not more than 5 minutes. If we would not have used it, then it would have been a process which would have taken uh, months. Okay, so this is the amount of reduction in time that we can get. Now, once we have the final geometry of the machine, we did the detailed finite element analysis. Okay, and did some kind of fine tuning if it's necessary, and got the final design. And this is how the final design of the machine eventually looked like. Now, one thing I have to keep in mind, I have to emphasize, is that the quality of the results that you get from the machine learning algorithm, the neural networks fall in the category of machine learning. So the quality of the results that you get depends on the quality of data that you have used to train it. Okay, so if you have used a bad set of data to train the machine, to train the neural networks, then you can't expect beautiful designs. Okay, but if you have used a very high quality data to train your neural network, then you would get very good designs, initial designs. Okay, so it's something like, we can imagine that this neural network, or this entire machine learning and AI in general, is a very bright student, a very bright kid, If you teach it wrong things, it would do wrong. If you teach it great things, it would do wonderful work. Okay, so everything depends on the type and the quality of data that we are going to use. But yes, once trained on a high quality data, the subsequent job of designing becomes extremely easy. So you can reduce the time taken to come to a design from months to actually a couple of days. So that's the order of reduction in time that one can expect. So this was actually the last slide that I wanted to discuss with you. So eventually we will have a complete design platform, okay, which will start with the very high level problem statement, would do an automated dry cycle analysis, would extract the critical parameters of the machine, would use the relative the three neural network models. All that will be integrated onto a single platform. And we are trying to put everything on Java platform. We are trying to use, so not Java, sorry, Python. So we are programming everything in Python. And then at the end, we would have the motor design. So from this high level problem statement to the final motor design, would be one seamless platform, and all the intermediate steps, all four of them would be actually encapsulated in a machine learning and AI paradigm. So that is what we are developing, and hopefully in near future we will have our own design platform. So I think with this I will end my talk and would open the platform for Q&A. So I hope I could make some sense. And yeah, it's a big topic, but I guess people might have appreciated the initial idea.
Yeah, Dr. Praveen Kumar, it is a really excellent, eye-opening, very good presentation. And I really appreciate the way you have explained it, even for a, layman kind, even they can understand it, very easily. I really appreciate that.
Thank you.
Uh,
Thank you very much.
I just have one question to,
Mhm.
ask for. I think in one of your slide where you have taken the inputs, maybe if you can just show that slide where you have taken the inputs
Just a second.
from the different machines, if you can just show that. I just
Mhm.
wanted to understand now, I'm sure, I think it must be from the, I think probably by the end of the time. Yeah, this one. Yeah. So I
Hmm.
think the machine, I think, must be of the same type, right? Suppose you're trying to make a, suppose I don't know what kind of a machine I need to design, whether it should be PMSM or,
Oh, yeah, yeah. This neural network was trained for induction machines.
Okay. No, yeah. So my question is basically, yeah, that's good actually. But suppose somebody wants to know,
Hmm.
which kind of a technology he wants to choose. So there's one way is possible is that he can try all different machines in one learning, and take an output. I
Um,
don't know.
no, no. For that, that's also a question that we are trying to address using AI and ML. Now, for a given problem statement, we can use an induction machine, we can use a permanent magnet machine, we can also use a synchronous reluctance machine, we can use axial flux, we can use radial flux. Now, the question comes that which one should one be choosing? Now, that is a problem which needs judgmental models, because you have to judge various kinds of technologies. Now, for that, we are planning to use AI. We have not yet tried for the motors so far, but we think that we will have to go for something which is known as natural language processing. So the idea is that there is a lot of literature available from different experts who have given their opinion. Now we have to collate all that literature, and we have to train a natural language processing based algorithm, and then that algorithm would interact with the designer. So
Mm.
you ask that algorithm that I want to design a 50 kilowatt motor for my EV application. So which motor technology do you propose? Then it would start to answer that, well, every motor technology has its own advantage. If you want a very compact machine, then go for an axial flux design. But if you can compromise with the weight and the volume a bit, go for a radial flux machine. because radial flux machine would be cheaper to make and so on. So it will do such kind of an interaction with the designer. It is feasible, needs a lot of data, needs a lot of input, but it is doable, and we will be doing it, no doubt in that.
Okay. Thank you. Thank you. Thank you for the answer.
So I hope I could answer your
Oh,
question,
no,
Mr.
no. I think
Vijay.
you answered me completely. Thank you
Yeah,
very much. You understood my question and you answered it. Thank you very much.
yeah. So any other questions from the audience?
Yes, sir. We have one more question in the chat box.
Okay.
The question, so is the question visible to you?
Yeah, yeah. Sir, is this method suggest type of motor? No, so far no. This because this was trained for induction machines, and I think this was the question which Mr. Vijay asked, and I explained you. So that's a different level of AI algorithms that we would have to use. Okay. So, are there any other questions?
I think I have one more question.
Yes.
I want to know, like, as of now, globally, where, which all company, is everyone using it, or, how much it is being used, and which all are the leaders in this?
Oh, that is a very tightly held secret. So I'm not. I don't know who
Okay.
is using it or how many companies are using it, but yes, what I know is that this is now becoming a new paradigm shift in design of systems. So we are looking at just motors, but it can be extended to batteries, to inverters, to many areas, to the entire drivetrains even.
Yeah, complete drivetrain. Yeah, it can be for the
Yes,
entire drivetrain, or.
yes.
Correct.
So
No, I think it's an excellent concept.
yeah, it just needs a lot of time and patience, that's all.
Yes, yes, yeah.
So yeah, any other questions from the audience? I would be happy to answer them.
So there's one more question in the chat box.
Yeah. In the Q&A. No, okay, it's in the
In
chat
the
box.
chat box, you said.
Yeah. What are the performance parameters which you are planning to optimize? You see, performance parameters we can't optimize because performance parameters are the requirements of the vehicle platform. So if the wheel needs 30 kilonewton meter torque, then that's it. We can't do anything. What we try to optimize is the size, the weight of the machine, keep the efficiency as high as possible, and reduce the cost of manufacturing. So those are the parameters that we try to optimize. Uh, the next is, can we maintain the fuzzy logic program? Yeah, well, fuzzy logic is not directly applicable here for the design of the machine. That is used for the controller part. Yeah, are you considering torque ripple? Yeah, of course, torque ripples have to be reduced, both the electromagnetic torque ripple as well as cogging torque. Okay, they cannot go beyond a certain value. But then also we need not be very finicky about getting a straight torque profile. Okay, because anyway, the vehicle will experience a lot of undulations on the road. Okay, they would create a lot of ripples in the torque. So as long as your ripples of the motor are lower than the undulations on the road, we are good enough. That's not a major concern after that. Okay.
One, sorry, one more question.
Yes, yes.
So I think this can be used very well as a validating tool. So whatever is, coming out, so you can keep whatever you're designing, right? So it can be the whole cycle of this ANN can also be, developed as a validating tool,
Yes, it is possible.
right? So,
Yes.
it's a cycle, whatever you are, and then you're further improving your, logics of, your programs, right?
Yes. Yes.
ANN programs.
Mm-hmm.
So that's very interesting.
Yes, it can be done. It can be tweaked to do that job as well.
Yeah, 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 yeah.
Yes.
But you said very rightly, it's very, very important to, have the inputs correctly,
Yes.
because it's garbage in, garbage out. Very, very important that.
Yeah, yeah, that's true. It's garbage in, garbage out, no doubt in that.
Yeah.
Yeah. Okay.
So what is the status as of now for this one at your place?
No, it's going on. The development is still going on. I think some of these students are already in this meeting as well. So I think in 2-3 years, maybe we will have a very good, stable, robust platform.
That's good.
Yeah.
Good. Thank you. Thank you.
Now there is a question from Renish Jain, and the question is where we can get the data for new technology motors like SRM for EVs. Yeah, one has to talk to the OEMs or the manufacturers of those motors, and one has to do a lot of testing on them before we can get the data. There is no escape from testing, because only testing will tell us what is the true performance of the machine. Now there's a question, sir, EV company shifting towards PMSM or reluctance motor, then why you develop this for induction motor? Oh, well, EV industry is moving towards PMSM machines because they are easily available and readily available from China. But all serious countries in the world, like the European Union or North American countries, are moving away from magnets to ensure that they have a robust supply chain of the critical materials. Okay, and there the induction machines are becoming very, very serious in EV domain. So maybe in India people might not use it for the time being, but in other countries they are becoming the machine of choice.
Is that the reason primarily, Praveen, Mr. Praveen, is because of the acoustics reason, the noise,
No,
as
no,
well as
no,
the
no, it's not
efficiency?
the noise. It's neither the efficiency as well. It's just about that PM machines were readily available, so everyone went towards them.
Yeah, I understand. So I mean to say today, induction machines, see, India has been making these induction machines from long time everywhere, right?
Oh, that can't be used in EV applications. Those are all industrial machines. So there's a big difference between the industrial application design and EV application design.
I
The
mean,
entire design philosophy is completely different. The geometry, the shapes, and so on are very, very different. So if once done properly, then induction machines are not bad compared to the PM machines.
yeah,
They
yeah.
have,
So, yeah, my
yeah.
point was basically that, there is something available, now it has to be, moved to this. Yeah, there must see, there is one case where you don't have anything. And in another case, you have something, and from there, you need to migrate to, EV requirements. So it's my opinion as a layman, it should be easy to progress.
Yeah, with induction machines, it's very easy to progress, no doubt in that.
Yeah, yeah.
Yes,
I,
yes.
yeah, I think more research is required, and more, I think, fine tuning is required.
Yeah. So I think there is some more question. One question is from Saptarshi, and the question is: are you optimizing stator lamination thickness? Now we have an option of only two lamination thicknesses: 0.5 millimeter and 0.35 millimeter. That's it we had. So there wasn't much that we could do in the lamination thickness optimization. Okay. So are there any more questions which I might have missed?
Yeah, sorry, one more question from my side. I think
Yeah,
so.
yeah, yeah.
It was such an interesting, presentation that, there are a lot of, questions are coming to your mind. So I'm not able to stop that. How about those magnet, type of magnets? Is that also will be taken care, or it as of now?
A type of magnet in the sense?
I mean to say there are various types of magnets, right? and their size and all, will that also be
Yeah, it
taken into
depends on the
account?
training data. If you have motors with different types of magnets in the training data, then it would be taken care of.
But in your study currently, is it in the scope or no?
No, no, not yet, because we
Okay.
don't have the data so far.
Okay. Hmm.
Yeah.
Thanks.
Yes. Yes. Welcome.
So if I understand, so
Mhm.
there are totally three set of ANNs, right?
Yes. Yes.
That can be maybe these stages can be a little more also. Maybe going forward, you might realize that okay, we may right now we have put three ANNs. We may have
Hmm.
to add two more or like that.
Yeah, that can happen. That can very well happen. Yes. As and when we progress with the design,
Yeah, yeah,
so it's possible. And moreover, I think for different motor types, there would be different ANNs. There
correct.
would be an ANN for a set of ANNs for induction motors. Similarly, there might be for PM machines, for different categories of machines, we might have to do that.
Yeah, yeah,
That
good.
is very likely.
Yeah, okay, thanks.
Okay. Yeah. Uh, Okay, there is a question. Any alternative to PMSM motors for Indian conditions? Yes, induction motors is a viable alternative. Why not? That is an alternative.
So,
Okay.
Mr. Praveen, this is asking one more question. What is the issue? What are the see why is that induction machines are not getting much in use in India? What are the bottlenecks? Is the design or
Yeah, it's the design. And in India, we never had any know-how in EV. We were all just importing the kits and assembling and selling it. So whoever sold us cheaper was it. That was
Mhm.
it. And our supplier was mostly China. So whatever we got from there, we used it.
But if I understand well, I think Tesla is also using induction motors someplace, some
Yes.
of the
Yes, because
right.
they started to realize that there's no point using rare earth magnets, and they have started using induction machines in some of their models, which is very successful actually.
Yeah, yeah. Okay. Hmm.
Okay,
Yeah, good. Thanks. I think very nice to.
thank you very much. So I am not sure whether there are any more questions that are there. Okay, if there is one question, it says if there is less data available, then what is the way to reduce the time to design a motor? Well, if our training data is less than the minimum threshold, then it becomes a very challenging problem to train the neural network. Now, how much is enough is a question which I can't answer right now. Maybe with time, once we have more experience, I would be able to tell you that how much is enough to train a neural network. So far, even I'm clueless about it.
And maybe from the last question from my side.
Yes.
Uh, See, like you are doing this in your IIT Guwahati, right?
Yes.
So you will also require a lot of motors, as inputs.
Hmm.
So are you starting from that stage where you're taking the inputs or you're taking this data from outside?
No, we take the data from our industrial partners.
Okay.
Yes. Because for us to measure so many motors and to have a big library is not possible. So
Hmm.
various OEMs, tier one suppliers, so they manufacture many motors. They test them for quality purposes. So that's our repository.
Okay. Understand. I got it.
Yeah.
Yeah. Yeah,
Yeah.
good. Thank you. Thank you.
Good. So I guess we have come to the end of the session, and just the final question which I can see in the chat box: can we use induction motors for scooter applications? Yes, we can use it. And maybe if you go to our LinkedIn page, we have presented many analysis for two-wheelers using even induction motors. So you will find lots of answers to your questions over there.
Is anyone using currently in India for this two-wheeler
No,
induction
no,
motor?
no one, no one.
But see, one thing is there. Suppose, for example, it's a bike, right?
Hmm.
So people in the bike will definitely prefer some kind of a sound, you know.
Yes.
And I think there is a regulation also, I understand, coming in Europe, where they are saying that the vehicle should not be silent. There has to
Yeah,
be some
because it,
noise.
it, it can create an accident.
It can create an accident. Yeah.
Yeah.
So, I think there is a regulation coming up. So
Yes,
that
yes.
way, it makes, I can understand, people have a feeling that, it should be silent, right? But if there is a noise, okay, from my understanding is that noise is one of the biggest issue in induction motors.
Hmm.
So that
Hmm.
induction motor can be used in motorcycles, right?
Hmm.
Motorcycles also doesn't have a problem of size, big.
Hmm.
Let's say, for
Hmm.
example, I'm talking about 350 cc, 600 cc, the
Hmm.
size is
Hmm.
also not an issue. So there it can be very successful.
It can be successful even when you need a very noiseless operation, because the motor can be made very silent as well. It's not at
No,
all.
I'm just saying, let's say today's situation,
Hmm.
people say that, induction motors are normally more, noisy, right?
No,
So,
no. I mean, the EV motor, the induction motors developed for EV applications are not noisy at all. Not at all.
okay.
They are very quiet.
Hmm.
They can be made noisy, not a problem. But generally, they are very quiet.
Hmm. So the issue may, okay. Hmm. So I think we can expect more and more induction motors in the two-wheelers, three-wheelers in coming days,
Yeah,
right?
we should be encouraging
Yeah.
that. Yes.
Okay, good. Thank you.
Yeah. Okay. So Kushagra, I think I don't see any more questions. Am I right?
Um, yes, sir. There's one more question that has come up, like
Okay.
by Renish only in the Q&A chat box.
In the Q&A chat box. Okay. What is the question? What will be the design procedure to follow if no such data is available, and what if we want to reduce the time to design? You see, we won't be able to reduce the time to design. We will have to follow the conventional procedure to design the motor, which I showed you in the second slide, the entire design process. So one has to go through that, and that will take time, many, many weeks, if we don't have enough data to train the neural network. There's no other shortcut for that. Okay,
Yes, I think that's it. That's all. That's
fine.
all.
So I think with this, we have also come to the end of the session as well. I think it's 11:30.
Yes, sir.
Yeah.
As the session comes to an end, I would like to express my gratitude to our honorable speaker, Dr. Praveen Kumar, for delivering this insightful session on machine learning and artificial intelligence for EV motor design. I would also like to thank all of our audience for being a part of this session. And I'd also like to thank all of our seniors at Mars Foundation who have directed us to bring such an informative session and bringing sustainable mobility at front. At last, but not the least, I would like to thank Machine Maker for organizing this event beautifully. Thank you, everyone. Thank you
Thank
so
you.
much.
Thank you, everyone. Thank you. Have a good day.
Yes, sir. Thank you.
Thank you.